Christian Filling, and I'm a programmer at 2468. And presenting with me is Jacob Henderson, also from 2468.
All right. You may be asking yourself, what is automation? And automation itself is defined as programming the robot to perform a task without manual input from a driver, operator, or human player. It's used very widely in a lot of FRC purposes, but most commonly used during the autonomous period of each match, where the robots are required to use automation. But like I said, it can also be used to speed up some other aspects of the game, which I will get into later in the slides. So there's a couple advantages of using automation. A lot of these include auto, like I mentioned before, where you can maximize your scoring in the autonomous period. And since it's double points, getting the maximum number of balls through the inner or outer port as you can is a very valuable and essential part of winning any match. You're also able to speed up cycle times with automation because you're able to locate and pick up balls easier using things like ball auto align. And this can once again help you out in auto because it'll allow you to increase the number of balls you're able to cycle during those, during that autonomous period, which is going to help you get more points as well. And furthermore, automation is also helpful because during teleop, you can keep your turret constantly pointed towards a goal by utilizing an IMU and making sure that your turret is facing straight forward by counteracting the degree that you're turning with the degree that you turn the turret, which allows you to lock onto a target much quicker than you may if you just don't do that at all. So some examples in automation in FRC are subroutines. For example, cycling by picking up balls and shooting them could be considered a subroutine. And if you can automate that, then you'll be much better off because you won't have to rely on inconsistency or things that you can't rely on. You'll be able to safely say that you can successfully do this task and you can do it quickly and effectively. There's also examples like path planning. You can draw out paths and you can utilize them to maximize the scoring that you do in auto. And then furthermore, like I mentioned, ball auto align previously, as well as trench auto align, which can be used to help you align with the trench if your driver may be more inexperienced and may have trouble lining up that very tight gap.
All right, so on 2468 specifically, our main uses of automation is that of the path planner, and this is used to automate the creation of autos. And I'm gonna hop over to LABView to demonstrate it. All right, so this is the path planner, which we made about 4 years ago, and we've been making improvements to it since. And so if you can see my cursor, the section right here is where we draw paths. Like say we can add points and we can delete points. One thing to note is this image right here is actually just a cropped image of the field from the game manual. And we have a config file right here that specifies the width and the height of this in real world units. And that allows us to scale our path properly. Another thing we can do is we can also move where the bot starts around or on this image. We also change the angle. Now, however, since the path's all relative to the bot, so this is only used to help us visualize the path and doesn't actually affect how the path runs. So up here on the top left, if you can see my cursor, there's a section for like saving paths, making new paths and whatnot. Say I wanted to save this path, I could save it, and I could open it again. Okay, that's not supposed to happen. Well, anyways, it normally would work, but I can open up other paths too. I can delete stuff. I can open up the folder where the paths are located to delete stuff if I wanted to. And so now I'll mention some properties of our path. So one goal of our path is to provide a relatively smooth path with a with a continuous jerk. So one thing we do to this is we try to maintain a constant velocity. This doesn't necessarily give an optimal path in terms of velocity, but it's pretty smooth. So as you can see, our path is a variety of different colors, and I'll talk about what each of those means. So the blue is indicating that we're turning a section of the path. the gray is driving in a straight line, the green is accelerating, and orange is decelerating. And as you see in the bottom left, is actually a graph of the velocity over time. As you can see, besides the initial acceleration and initial deceleration, the velocity is constant throughout the entire path. Also over here, we have a duration, which is an approximation of how long this path will take to run, or how long it take to drive, and then a distance. There's also a play button, which will show our bot on the field running through this path. And another thing we can do is we can drag it to a certain point within the path. Now, sometimes if you draw a path, it'll try to maintain a constant velocity, but given how some points might be, it might not be possible given a target velocity. So as you can see, it's all out of whack, and this auto smooth button turns green, which basically means it's an invalid path and we need to smooth it. So this auto smooth, it'll set specific accelerations at certain points to try to get to every point. As you can see, it can't really do that despite the change acceleration, as this point is not really attained. These like the user-defined points are more of like targets to go to rather than like definite points. But there's ways to like try to ensure you get closer to it. So up here, if you can see my cursor, there's a little limit section. This defines the max velocity, acceleration, and jerk. As I said before, since velocity is constant, you could treat velocity as more of a target velocity. And so say we wanted to get closer to 0.3. Well, what we do then is we just lower velocity, say to like 2 instead of 5 feet per second. As you can see, our turns are a lot shorter, and then we're driving a lot more straight lines, but we actually get to all the points. But currently, an issue for Path Planner is that we can only really go at one velocity. We're working on a version to kind of have multiple velocities at different parts in the points, but currently it's a bit buggy, so we're currently just using this with only has acceleration overrides. And yeah, so down here you can manually choose accelerations. We don't typically do this. We usually just let up AutoSmooth do it, and it works pretty well. Also, you can change the max acceleration and max jerk. And for those not familiar with jerk, it's just the change in acceleration. So say if we had a lower jerk, you get a much smoother path on the initial acceleration and deceleration, and we smoother path overall. If I made it higher, we have a much more trapezoidal path. And generally, we just try to do a jerk for whatever our highest jerk is our bot can handle, depending on like the center of gravity and whatnot. Also above those limits are conditions for initial velocity and final velocity respectively. Like say I set initial velocity of 5. As you can see in this velocity graph, it starts out at 5. And we can also set a final velocity. And this is mainly used if we want to splice paths together. Like say you want to run a path and then call a different one depending on like different conditions of the game. And it'd be nice to not stop between those different paths, which is why we have that. But typically, older autos are their own individual path, so we don't use this very often, but it does have this functionality. We also have some parameters for setting up the bot on the field. We have a snack robot to baseline, which makes the bot stay on the bottom of the image, which isn't quite too useful for this game, where the baseline's all the way up here, but it has been useful for other games. Additionally, you can stack robot to foot, which basically means when we try to move the robot, it'll like kind of move by foot instead of normally having more precise movements. We also have an angle limiter because we can rotate our bot, and it'll rotate by 15 degrees normally, but we can change that. But typically, a 15-degree limit has been sufficient for most of our paths. We also have a sample period, which is basically how often the points from the path are sampled and stored into the path file. I'll talk more about that later, Howard. On the right, we have a command palette. And this allows us to put commands into the path, which is pretty useful. Say if we didn't have a command palette and we couldn't run commands in our path, we'd have to run a path, stop, do a command, and run a path again. And that leads to a lot more code, a lot of messy code, and a lot of bug code as we've experienced in the past. Up here, we also have a command sequencer for you can choose your project, you can refresh commands, and you can also, oh, I shouldn't have hit that. It takes forever to refresh commands. Yeah, so We can also, so we can put commands that were in part of the path. Just say an example command drive for time, not really useful path, or not really useful command to have in a path, but it's there. We can also drag the slider to move our bot to a different part of the path, and that's how we put in commands at different sections of the path. Now I'll talk about how we generate the curves to turn with. So this is an Euler spiral, or rather just a part of an Euler spiral, since the full graph is not too useful for turns. It's just the beginning part. So what it does is it takes a point at 0, 0 and generates a blend of part of the Euler spiral, and then it reflects it along this point. And this was used mainly in the 1900s for railroads, and so that when trains would turn on railroad tracks, they wouldn't tip over. And when used in our bot, it generates smooth paths that it doesn't jerk our bot around too much. So the variables up here, just for demonstration, there's t, which is related to the angle. Like the higher t, we turn at a much sharper path. And you can see the actual tangent angle down here. Additionally, we have a scale magnitude, which is kind of related to the acceleration and velocity. If you need to make a wider turn, then you need a bigger Euler spiral, and a smaller one if you didn't need to turn as a lower acceleration. I'm going to hop back to the slides to talk a bit more about this. So about the curve generation, as I said earlier, we generate an Euler spiral from 0, 0 to this point x1, y1, and then we just mirror it along this axis that bisects point B. And the length of this spiral is actually equivalent to these two segments down below. It's kind of getting covered up, but x1 and x2. And so each point in our path has the data of a point x1, y1, and then an angle theta b, which is just a navigation angle, and is defined right here. And since our curves are represented in an Euler spiral, which is based off Fresnel integrals, which is a continuous function, we can't really store that in memory, and generating points at runtime would be too expensive and be bad for latency and just not needed. So instead, we choose to sample points every 20 milliseconds to align with robot code, which allows us to store it easily. Also, one thing I forgot to mention, one usage of our path planner is actually to tune PID for our drive base. So what we usually do is we'll draw like a squarish path. Oh, okay. And then we usually set a pretty low velocity for this. And then, we'll have it like drive in kind of a square shape, and then we'll just keep it running, and we'll tune PID while it's running. We'll look at the graphs, and then once it can drive in like a square shape or return pretty consistently, we know it's pretty good. It's also useful to tune our IMU, or to test IMU accuracy, because we use an IMU along with our path angles to make sure it's maintaining the angles it's supposed to. And I'll talk more about how we should drive to a certain angle. So for a small period of time t, the bot moves f units forward. And then, so to account for the angle, we need to drive some difference between the right side and the left side. Like one needs to drive more than the other. And so we define some distance d. So once I drive f plus d, I'll go do f minus d. And d is defined as, since, I'll mention the triangle in the left diagram is similar to these two smaller ones. They have the same angle theta. And because of that, we can define d as w times tan theta, where w is half the width of the bot. And in fact, this is the main thing pretty much the only thing we have to provide to the path planner as far as physical bot parameters go. Of course, we also have to tune for like wheel friction and other things, but that's not specific to the path planner itself. That's more about driving it.
So now I'm actually going to go ahead and screen share some LABView, and then we can head back to the slides after that. Does that show up?
Yeah, I can see it.
Okay. So this is our 2020 robot project that we made last year for Infinite Recharge. I'm just going to go over some basic implementation of how we used our autos and how we would program them if we're just talking on a baseline level. So we're going to head into robot main, and in here there's two VIs that we're going to be looking at. These are called auto setup.vi, which is this one. And then we're also going to be looking at another VI called auto runner.vi. So if we open up auto setup, we'll see, a decent amount of code. But what it does is fairly simple. All it's really doing is down here, it's taking the input as a file path, it's stripping that down, and it's storing that into an array and writing it to a table like the network tables so that we can access it later in the code. And then up here, we're accessing those file paths, and then we are using some different blocks and VIs in order to extract that data from them. And so we can pass that on to the robot. And so we're able to access it later on, and we're able to use those paths how they were written. And we get the data with this get data block, and then we write it to this global variable called auto, which, as I will show later, is accessed in order to run some different autos. So that's really all there is for the auto setup VI. So if we exit out of this and head back to robot main, we can open up auto runner VI, and you'll see here there's nearly no code here. And this is on purpose. Most of the code here is in this VI, which is called play path. And play path does exactly what the name would suggest. It actually takes a file path as input, and it plays the path. It tells the robot what to do. It gives it the instructions it needs, and it allows it to actually run the path that we drew. And you'll see that auto global variable that I mentioned earlier, it pops back up right here, as well as another global variable called first path, which will be mentioned later in code. So that's really all I wanted to say for auto runner VI. I'm going to head back to the project structure right here, and we're going to see, we're going to actually go into the drive controller now. This code doesn't compile quite yet, or it doesn't compile right now. There's a couple broken wires, but all we really care about is this VI, which is called calculate velocity set points. So we head over to the block diagram. It's kind of a mess, but we're only going to go over some very specific parts of it, just the most important parts. So we'll see right here on the left side, we're taking input of velocity data and angular data, and then we're proceeding to index those and then utilize those to calculate some different angles that we're going to need in order to use our autos to their full extent. And then further, we're also checking to see if the path is reversed, because a lot of times if you're running a path, you're going to want to reverse that path to get back to where you came from. And so we can run a path and then turn reverse on, run it in reverse, and we'll be back on the baseline where we started, ready to shoot. We also use the IMU up here in this top section, and that's mostly used to kind of make sure the robot stays on track. It tracks the angle, and it makes sure that we are sticking to the path that the path planner drew out for us, and so we're able to stay on that path and do what we expect the robot to do pretty easily. Next, if we move over a little bit, we're going to see some numbers, and I'll explain more specifically what they do. This 20 right here is a very important number. It's the wait time between each command. And that basically means that we're going to wait 20 milliseconds before we calculate new velocity set points. So we calculate one, and then we wait 20 milliseconds and calculate another. We do this so that we can constantly get new set points, and so we're able to update our robot with new information repeatedly. And you'll see that that feeds right into the wait time milliseconds output right here. We also have this number that's the fudge factor. And this is going to be different for each robot. It's kind of just a robot or it's just kind of a number we tune for our robot specifically. It's going to be different depending on the weight, height, and size of your robot. And we use it specifically to calculate angle values for the robot to turn to, so that we can stay on the track that we set out for ourselves in the path planner. So that's all I wanted to talk about in this 2020 robot project. Next, I'm actually going to talk about some PID. So this drive controller is just kind of a basic subsystem we drew out. It doesn't actually have any real purpose, but it's just opening a SparkMax motor controller, and it's setting its output, and it's getting the voltage, and it's plotting it onto a waveform chart, which is just kind of a numeric indicator in like graph format. Um, so like Christian mentioned, we actually tune PID using a square path. And using that square path, we can make out a bunch of different graphs like this waveform chart. Usually we'll have 3 to 6 of them, and we'll be able to check to see if the p-value is too low, or if the I-value is too low, or d-value, etc. And we'll be able to correct them and make sure that we tune our PID to its fullest extent. And so we're able to make our robot function efficiently and stick to the path that we designed for it. So I think now we're going to head back to the slides. If you want to screen share, Christian, we can talk more about PID. So we're going to talk just like a little bit more about the general use of a couple different concepts like PID. And like I mentioned before, the purpose of PID is to kind of account for the error that accumulates when you're constantly running autos or driving the robot or just anything teleop or auto. There's lots of uses for PID, and we make sure to use that specifically. This is kind of an important topic, and it's yeah, like I said, it's used to account for the accumulated error. There's 3 different terms in it. There's P, I, and D, and each needs to be tuned separately. Otherwise, your robot may get a skew in its path running. So some other math that we used in our robot code is just basic trigonometry. We use this throughout our robot code in auto and teleop, all throughout to calculate limelight angles, use different paths for the path planner. Trigonometry was a very important topic that we used heavily, and it's very important that you have a baseline knowledge of that at the very least. It's also very important that you understand gear ratios, and you talk to your designers a little bit about what gear ratios are on your motor. And so you can account for those, and you don't end up burning out motors by giving it too much power and making it spin too quickly against the gear ratio. And this is not an extensive list. This is just kind of a couple things we thought might be important to know. There's obviously going to be different things that you have to tackle if you decide to create autos or create your own path planner or other similar things. Different math is going to be involved for different issues and all sorts of things. But for now, this is just what we thought might be necessary to talk about in this presentation.
So yeah, indeed, we got a few questions. I don't know if you're ready. I may get started reading them to you.
Yeah, go ahead.
Yep. So the first one says, how long have you been working on this path planner? I think it's referring to the one we saw a few minutes ago.
We've been working on our path planner for about 4 years now, and we constantly update it every year, changing little things, making sure it can run a little bit more efficiently. But we first created it around 4 years ago.
Okay, well, the next one says, what do you guys use PID for on your robot?
Christian, do you want to take this one?
Yeah, so we use PID to account for errors in machine motor set point in the actual value. Like say you're driving say you're using PID for drive base, and you go over a little bump where you have some unexpected friction, you have error in where you expect to be and where you actually are. PID will give you a new set point based off this error to account for it and get back on track. But it could be used for things besides like a drive base. It could use it for a few different other subsystems.
Okay, well, then we got another question. Anonymous, the three last I read you were anonymous. So for implementing PID, do you need extensive knowledge of calculus, or are there functions that make it easier?
Generally, some encoder libraries like SparkMax will have a PID function built in. And as far as tuning it, while it's definitely helpful to understand the math behind it, which is based on calculus, you can tune it based on just looking off graphs without needing to know any of the math. Of course, there's different ways to tune it, which might require more or less math.
Of course, okay. Well, another question. Do you guys have any plans for adding to the path planner?
Yeah, so as I mentioned earlier, our path planner tries to go at a constant velocity. We're trying to add a feature to where we can choose different velocities at different points in the path, so we can have a more optimal path. But currently, we have some bugs with it, but it's definitely something we're going to add.
Awesome. So, while we get more questions from the public, I don't know if you could tell us a bit about your team and maybe one or two tips you could give any rookie team or all the teams that are watching you to improve their skills overall in automation, but also in any other topic you consider important.
I would say specifically for auto, it's important that you do a lot of testing. Testing is constantly something that we have to work on, even as a team that's not a rookie. As long as you are able to test things and you give yourselves plenty of time to work through the issues that you may encounter, you should have no problem creating good autos that can score you, 15, 20 points in the autonomous period, which can give you a great boost up at the beginning of every match.
Another tip I could give would be to document your code. As you saw in some of our code, it didn't have as many comments as it should have, and generally makes code harder to maintain. And if you have bugs, it makes it a lot harder to debug if you don't know what the code does, and you have to figure out what it does every time you look at it.
Excellent. Well, thank you very much. Well, we got another question. For a team that doesn't have a path planner, how do you recommend going about planning and making autonomous paths?
So LABView has a VI called the autonomous VI with every new project you create. And it would probably just be a process of trial and error, setting motor values for a specific amount of time, or allowing your intake to intake for a specific time, or making sure that you can test that over and over and over again. But it would just be placing down VIs and making sure that you can account for what they do and when they do it.
Generally, you probably want some basic functions to get paths, not in the path planner sense, but like a function to drive a certain distance, to turn a certain distance, and then obviously to do other intake and outtake stuff. Generally, it won't be as optimal as like a well-designed path planner, but it certainly could probably get the job done. But of course, it would require a lot more trial and error.
Yeah.
Right. So, well, we can all confirm that 2020 was a wild year. There weren't a lot of things that didn't go as planned. So what are team appreciates goals for this 2021? What are your plans, guys? What are you expecting to change or improve in this year? I don't know if you could tell us a bit about it.
Well, for one, we're planning to make an entirely new bot. So I guess, and hopefully one that's better than what it was last year.
And we're also hoping to improve upon, not just make a new bot. We're also hoping to improve upon our past team. They obviously had a lot of great accomplishments. We won chairman's at Greenville, and we're hoping to continue that, and hopefully, make the chairman's finals and attempt to make it to Einstein. But that's a goal for every team, of course.
And as far as our code goes, we're looking to rewrite more code this year than we have previously. Like a lot of our code is reused from year to year with minor changes. We're planning to do a bigger rewrite.
Awesome. So, well, I think we are done of questions for the moment. I don't know if you get any other remark you'd like to say or any final comments so we can end your participation in today's conference.
Great. Thank you so much.
It's been an honor to have you with us today. We wish you the best, and we're expecting to, well, see you in the game field this 2021 season. Both of you, Jacob and Christian, we wish you the best of luck for you and the whole team at Appreciate 2468. And, well, thanks for being here with us. It's been a pleasure to meet you.
Thank you for having us.
Thanks for having us.
We'll see you soon. Thank you very much.